Our world is run by these incredible invisible forces. We're talking about powerful electric and gravitational fields that shape, well, everything, from how planets orbit the sun to the actual sparks firing inside our brains. So how in the world do you get a handle on them if you can't even see them? Well, it turns out the trick is to create a very special kind of map, a map for a world that's completely invisible. And that's really the big question we're tackling. How do we draw a picture, a useful map of this invisible landscape of force and energy? And what's cool is, the answer is kind of hiding in plain sight, in an idea that most of us have seen before, even if we didn't realize just how powerful it was. All right, first things first, we're going to step away from all the heavy physics for just a second and, believe it or not, go for a hike. We're going to use a simple tool that you've probably seen 100 times, a topographic map, to build our intuition. So when you look at a map like this, you're probably just thinking about hiking, right? But it's actually way more than that. This is a map of gravitational potential energy. Every single one of these lines, what we call a contour line, connects all the points that are at the exact same height. Okay, so here's the key takeaway. If you were actually out there hiking and you decided to walk perfectly along one of these contour lines, you wouldn't be going uphill or downhill at all. You're not fighting against gravity. Your elevation, and because of that, your gravitational potential energy, it stays perfectly constant. So what does it mean when you see the lines all scrunched up close like this? Well, that's the map's way of screaming at you that you're on a steep hill. You're changing elevation really, really fast over a short distance. Yeah, if you dropped a marble there, whoosh, it's going to take off down the hill, because that's where the gravitational force is strongest. And on the flip side, where you see the lines spread way out, the change in height is super gradual. This is a gentle slope. Here, the pull of gravity is, a lot more chill. And this one simple idea, how close the lines are tells you how steep it is, that's the golden key. Remember that. Okay, got our hiking boots on? Good. Because now we're taking that exact same idea and jumping right into the invisible world of electricity. This is where that whole map analogy is really going to pay off. Think of this as our translation guide. In this new electric landscape, what we used to call elevation or height, we now call electric potential, and we measure that in volts. You can kind of think of it as electric pressure. And that contour line we were just talking about, well, now we call it an equipotential surface. It's the same exact concept, just for a different invisible field. So an equipotential surface is really just that, a surface where every single point on it has the exact same voltage. Just like walking along that contour line, if you move a charge anywhere along an equipotential surface, you're doing zero work. Its electric potential energy doesn't change one bit. Let's take a simple case, a single positive charge. The electric field lines, they point straight out, away from the charge. And the equipotential surfaces, they're these perfect spheres centered right on it. As you move to spheres farther and farther away, the potential, the voltage, gets lower. It's literally like you're walking downhill, away from the very peak of a mountain. Okay, now for something a little more interesting, an electric dipole. You see how the equipotential surfaces get all squeezed together in that space between the positive and negative charges? And what did we learn from our hiking map? When those lines get squeezed together, you've got a steep hill. And yep, that's exactly what's happening here. The electric field is at its absolute strongest in that region. All right, so now that we know how to read these maps, let's get down the official rules of the road. These are the fundamental properties that tell us how these equipotential surfaces always have to behave. Rule number 1, they are always, and I mean always, perpendicular to the electric field lines. The field lines show the quickest way down the hill, right? So the equipotential surface, which has no change in height, has to be at a right angle. Next up, they can never, ever cross. It's impossible for one single point to have two different voltages. And finally, the one we already know, their spacing tells you everything. Close together means a strong field, far apart means a weak field. And this leads to a super important, kind of special case, conductors. When you have a conductor and the charges on it have settled down, its entire surface becomes one big equipotential surface. Every single point on it has the exact same voltage. And because of that, the electric field right outside the conductor has to be perpendicular to the surface everywhere. It's just a fundamental rule. Okay, let's pause for a second. Time for a bit of a brain teaser to see if you've been following along. Let's imagine you found a perfectly flat spot on our energy map. If the electric field, which is our slope, is 0, does that automatically mean the elevation, the potential, has to be 0 too? And the answer, is a big, fat no. Which is kind of weird, right? Think about it like this. Imagine you're at the exact center of a charged ring. The electric field is zero because you're being pulled and pushed equally from all sides. Everything cancels out. You're on flat ground. But you're not at sea level. You had to do work against the ring's field to get a charge to that spot. So the potential there is definitely not zero. So this is all cool physics theory, but so what? Why does any of this actually matter in the real world? Let's take this idea out of the textbook and see how it works everywhere from keeping you safe in a storm to, well, to powering you. Well, have you ever wondered why you're told you're safe in a car during a lightning storm? This is it. This is why. The principle is called a Faraday cage. During a lightning strike, the metal shell of the car instantly becomes an equipotential surface. All that charge spreads out, and since the whole surface is at the same voltage, it creates a little safe zone inside with no electric field. Pretty neat, huh? But honestly, that's nothing. It gets way, way cooler than that. Because this exact same physics is happening right now, inside you, at the unbelievably tiny scale of your cell membranes. See, the inside of one of your neurons has a lower electric potential than the outside, and that difference, that voltage, across a membrane that's practically nothing, is about -70 millivolts. It's tiny, but it's everything. It creates this crucial little electric landscape. That tiny voltage difference creates an electric field, our slope again, that points into the cell. And that field is what directs the flow of charged ions through these little channels in the cell wall. And that controlled little trickle of ions, well, that's a thought. It's a memory. It's your heart beating. We are literally creatures that run on these tiny electric landscapes. So think about that. We started with a simple hiker's map, and it ended up giving us the key to see these invisible electric fields that keep us safe in a storm and literally power our own thoughts. Which really makes you wonder, doesn't it? What other fundamental, invisible landscapes are out there shaping our world, just waiting for us to find the right map to finally bring them into view?